Hello, my name is Eric Wiita, and I'm here with the British Gear Association to talk about how we mold gears at Victrex. And I'm a business development manager with Victrex. I've been with the company about 15 years. Most of that time has been spent in manufacturing, on repeatability, a little bit on part design, and then statistics and understanding gear performance. Thank you for your time, and I'm glad you're here joining us. So Victrix as a whole is where I'll start this conversation, and then we'll move it through into gear design and gear manufacture. Um, but Victrix, we're all about bringing change and coming up with just sustainable solutions to help the performance around the world every day. So to start with, we'll talk about Victrix and give you an idea of who we are and what we do as a company. So Victrix is the largest manufacturer of PEEK in the world. We have the largest capacity, and we own our supply chain from top to bottom. So it gives us the ability to control the polymer quality as we're manufacturing it. Now we have a culture where we're investing in R&D every year, not only to expand the variety of polymers that we offer, all in the PEEK or PEEK family, but also in the product forms that we make. So we talked kind of about partnership. As we've worked with people in the past, we've understood that they need PEEK to come in different forms or different structures to be able to release to the market and help them to do well in the market. So besides changing the number of polymers that we offer and the grades and varieties, we started to offer product forms through like filaments and sheets and other stock goods and tapes. And then as we continued to listen to the market and understand and grow, we've invested in companies or in manufacturing parts. So I was part of an acquisition, Victrix's first acquisition, where they bought a gear company, and we're located in Wisconsin in the United States, and we manufacture polymer gears. Victrix has also expanded what it offers through composites, and we'll talk about that later in the presentation. We have medical devices such as knees. These are like bone transplant plates. These are called trauma plates, which are used for if you have a bone fracture. And then we've got some pipe applications and aerospace applications, which are composites. So Victrix as a whole, I mentioned I was part of the transport business unit. That covers automotive and aerospace. But because my experience is in gearing, I really get pulled in kind of on every industry, and we cover and manufacture parts for all of these industries above. Every day, there's about 1,000 people who wake up and they're looking to innovate with PEEK and how it can be used to serve your marketplace. Victrix is also focused on the UN sustainability goals for 2030, and not only just on the environmental side, but Victrix is supporting me as I lead a STEM group. They help sponsor that group, and so right now I'm working with kids middle school to high school age, and we're building remote control airplanes right now for our current project. So we talked about where does Victrix serve or its markets serve, and a lot of people haven't heard of PEEK. It's used all over the place, but really just selectively. And so you probably don't know it, but PEEK is around you. You're just probably not aware of it. It's probably in your cell phone and maybe how we're listening to each other right now. It's used in seals for the oil and gas industry. There's over 500 million gears right now in the automotive industry that are made with PEEK. PEEK is used in medical devices all the time, and it's growing in that industry as well, in all of these industries, really. If you're not familiar with how polymer looks, this is what polymer looks like in kind of its granular base form. This is what we take and convert into gears and other molded parts every day. But PEEK comes in a variety of shapes, and so, or product grades. This is Vicoat, which is like a spray coating that can then be used to treat or seal a metal part for corrosion or abrasion resistance. We do have a fibers division. There's another acquisition where we're making filament. In Hill House, where our headquarters are, is where films are manufactured. And then this is just showing what a gear might look like, but we have molded parts as well, and then composite components too. So why would someone choose a polymer gear over a metal gear? And generally what we found is that you can see some benefits when switching to a polymer gear. What we have here is a demonstration where we took some metal gears and they were hobbed, and we've replaced them with a metal core on the inside for a press fit or perhaps a keyway, but a fit on a shaft with a polymer gear on the outside. This polymer reduces the mass around the outside of the part and really helps reduce the moment of inertia on the part itself. And it gives you this benefit against noise or NVH performance. So you can see a significantly lower moment of inertia on the parts, as well as less weight. And then with that NVH performance, this becomes an appealing solution to a lot of different industries. My primary focus is on, because it's transport, it's focused on aerospace or automotive applications. And we are looking at putting these into engine environments, so they're exposed to oil temperatures and high engine temperatures. So on the last slide, we talked about why might someone consider a polymer gear. On this slide, we want to talk about the different polymers that are out there. So there is a wide variety of plastics that are available out in industry to purchase. And all of them have different properties. And when you're going through your gear design, you need to select the correct polymer for your application. And factors that you're considering for your application can include temperature, loads, speeds, lubricants, as you're selecting your polymers. When you start in an application and you're selecting a polymer, you're going to start with some of the lower performing engineering polymers for cost reasons and manufacturing reasons. As you go up in your requirements for your gearbox, you'll eliminate those polymers that are available for you to select from. And what we find is that in the most arduous environments, that's where PEEK is left as kind of the clear performer over other polymers. So the factors that generally select for PEEK include temperature, chemical resistance, and mechanical strength. So when you're selecting your gearbox material, we're looking at that to understand what material makes the most sense to be used in your gearbox. Now, PEEK gear solutions, we already talked, they're used all over the place in cars. And in the green list over here are plastic applications where gears are being used right now in the automotive industry. And in the white, we're working on validating and getting them into production. So these are the ones that are seeing that engine temperatures with under load, exposed to oil. So very tough environments where polymer gears are doing well. So now we have this process. How do you go from your idea of a gear to mass production? And we'll talk kind of at a high level about what Victrex does and the site does, and then we'll have a little bit more specifics as we get on the next slides. So it starts with your idea for a gearbox and understanding where you're going to see your parts are going to see loading. With that, like we already talked about, we want to understand polymer selection. What polymer makes sense for you to use to manufacture your parts? And then it goes through a design loop. And I do have a picture of this later on in the presentation, but generally we don't have to follow gear design practices that you're used to in a metal gear. You can mold a direct replacement and make the same shape as you would have with a hobbed gear. But if you have flexibility in your gearbox, your housings, center distances, all those tolerances, we'd like to modify it so that we can take advantage of polymer properties. They do have a different thermal expansion. They do have, they're not as stiff as a metal is. And so we need to, if we can, extend the contact ratio on those. Once we have a design finalized, material selected, we could look at building prototypes or how you want to test this to go to market. So you can manufacture prototypes with a hob or with machining centers, which is what we do at our facility. And then somehow they're going to be tested, either at your facility or at our location. The parts can be tested to understand their performance. And after they're tested, then we look at saying, okay, how do we scale this for manufacture? That can be done with injection molding. And usually you'd want to look at higher volumes when you're considering injection molding. Otherwise, parts can be manufactured from like a rod stock or material stock that comes in a wide variety of polymers as well, and PEEK included, where you can machine or hob blanks from them. And Victrex is here to help you as you're going to market with that and going into mass production. So here's a bit more specific about what happens for a gear design. So like I mentioned before, we do gear design in Dantine software. We can look at outputs that you guys might have from other softwares, and we're looking at it for contact ratio, that root stress, and then we're also looking at tolerancing for center distance, and that growth that happens as the part is exposed to temperature. So making sure that thermal tolerances make sense. The parts are then analyzed for manufacture. Our team does a design for manufacture review because polymer parts behave a bit differently when you're doing your part design. We want to make sure we have uniform wall thickness, that you're going to have the correct number of gates and knit lines are in the proper locations. And then we'll look at how do we build those parts for you. This is an example of an injection molded tool. And on top of it is an injection molded gear, just to kind of give you an idea of what it looks like. This is a single cavity tool, and generally that's where you'd start with for prototypes. After the parts are molded, they go through an inspection loop where we're looking at the parts and understanding the shrinkage that goes on. That's what we have here in this square here. What you're seeing is a gear ring that's labeled number 1 that's made out of steel, and then down here number 2 is the molded part. There's this gap here that happens when you're molding. The plastic comes in as a molten polymer, and then it shrinks as it solidifies. When it shrinks away, we need to compensate the steel and our molding process so that it will consistently bring the parts to print. So once we have a process developed, we've got the steel developed, then the parts can go to mass production. This can be done, like I said before, with like a single cavity tool or multi-cavity tools, depending on what your annual volume needs are. So we make parts for customers that might have thousands of parts a year, and we make parts for customers that have millions of parts a year. Just depends what your needs are and what makes sense. Our highest cavitation that we have right now is 16 cavities, I believe, and for that we make millions of parts a year. We also have testing that we can do in-house. There's metrology, but then there's also some gear-specific testing we can do, or we can help customers as they do their final testing for product to make sure it's performing the way they want inside their gearbox. So at our facility, we do have in-house tooling capabilities. We have hot runners, which is a way for you to reduce cost as you're molding the part. There's like a sprue or runner that is generally considered waste, and if it makes sense for your application, we would look at a hot runner because it can eliminate that entire runner and just cut down on waste as you're manufacturing the parts. Where possible, we try to fully automate things so that manufacturing can be done kind of in a lights out operation. We do run 24/5 for our manufacturing cell. We have molding equipment that goes from 5 tons to 143 tons. And what that means in plastics is that your tonnage is kind of, it determines how big of a part you can make. And so with a 5-ton press, you can make parts that are small as about 1 pellet of plastic up to maybe 3/4 of an inch or so. And on our biggest press, we can make gears that are about 6 or 7 inches in diameter. For inspection, we do have gear-specific equipment and then just general metrology equipment as well. So we've got a gear roll tester. We have 2 gear we have a CMM and a gear GMM, both of which help us interpret gear geometry. And then we have our quality systems in place. So as we're looking to serve not just the general customer, but that automotive industry, we achieved our IATF certification. So that's a layer on top of ISO, if you're not familiar with it, which helps build that culture around continual improvement, risk mitigation, and manufacturing excellence. Talked a little bit about testing. So in this slide, I wanted to show a couple gear-specific pieces of test equipment that we have. This is called a single tooth bender. Some of you are probably already familiar with this. This device is used to apply a load. We have a lower anvil that fixes a tooth down here and prevents rotation. And then this upper anvil applies a load on a different tooth so that you get a downward force that's going to apply a load. You can use this to apply like a single tooth overload, like a yield or ultimate tensile strength sort of test, or you can use it to apply a fatigue test. It can't do a negative direction, so the force can't pull back up, but it can apply and then lessen the force and then apply again, so you can do a fatigue test. This test can be done at room temperature up to 150 degrees Celsius. We also have what's called a torque to turn device, or a quasi-static dynamometer. This machine is used to understand how a mesh would perform under a small angle of rotation. So this does not spin at high speed. It's not a full dynamometer. What you do is one gear is fixed to this back plate here. That's one portion of your mesh, and you can change the alignment. So this is the two gears are in line here on this one, and here is the gears would be offset. So I can move my one gear in and out to make it full alignment on axial, or offset for like a parallel gear set. Then you put another gear on this side. This side's what's going to apply the load, and this device applies that load, spins the gear up to 45 degrees of rotation while taking a lot of high accuracy measurements on displacement and torque. So then you could get an idea of what's happening in your mesh for movement and deflection inside the parts as you're applying a different load to it. Again, this can go from room temperature to 150 degrees C. Now, as you want to test your part performance beyond these small test rigs that we have in our facility, we have looked at other testing that's been done on engine dynamometers. So this is an example of a test that was done for durability. This is done in an engine. This is done in a fired engine test, and we've done simulated fire engine tests as well. And you can mate, we talk about configurations down here. You can mate a plastic gear with a metal gear, or you can do two plastic gears. You want to design accordingly. You want to make sure that your parts are set to mate with each other, and that you won't have excessive wear induced because of like an improper part design. But it is combinations that we have tested and run in both configurations. At the end, you can see that there is a bit of scuffing on the parts, but it's minimal. It's really the parts have been run, even though they've seen quite a few cycles in the application. Now, we talked a bit about that R&D effort and understanding that Victrex is always looking to kind of push that envelope, make market space, and understand what our customers want. So in transport, there is this, as you go up in ways that people have mobility, the demands go significantly higher for part performance. And you will get to a limit where it's not possible for polymer gears to operate. Some of these e-gear or automobiles with electric systems in them just have fantastic torque rates on them, and the steel gears on them have an incredible face width. That's a space where plastic really probably will never be able to operate, but we're always looking to say, where can we go and how far can we push it to be able to serve a bigger share of that market? And so today's polymer gears do have a limit on where we can achieve. And with our R&D efforts, we're looking to say, how can we expand? How can we move up? Knowing that we can't capture all of the market. There's a space where plastic just won't be able to operate, but how do we broaden that area? And so we've got some R&D efforts that we were talking about in here that will demonstrate for you some of those areas that we're using PEEK to do some pretty amazing things. So with that, I wanted to just mention that, like I was part of an acquisition in 2017, Victrex went on a joint venture with a composites company. And so TXV is Victrex's sister company in Rhode Island, or our sister company in Rhode Island, and they manufacture composite parts there. And we've been working with them in a couple different ways to span the gearing industry. So with a composite, we've talked a little bit about injection molding. Now we'll talk just a bit about composites and how it works. I mentioned several slides back that one of the things or forms that PEEK comes in is in a tape. So we take this tape, we have a low melt PEEK, unidirectional tape. That means it's a PEEK family chemical polymer, and we have carbon fibers aligned in one direction inside that tape along the length of the tape. And we placed that down in a woven pattern. So you can see on the base layer, it was horizontal, and then on the next layer up, it's coming in and out of the page. We have an automatic tape laying machine. It lays the tape down and it tacks it so that it's ultrasonically welded and held together. Then that plate is consolidated under temperature and pressure to make us a single solid piece. And then we have the option to not just leave it in that state where it is a solid, very hard, very stiff, very light material, but we can put PEEK over the top of it with injection molding. So it becomes a component that we mold over, just like those metal inserts that we had earlier in the parts. So this is representing PEEK being molded over the top of our green composite here. And in the end, what you get is a hybrid part. So we've got this combination of composite plates held together with like this ribbing or bracketing kind of configuration, just as this demonstration idea. And our team at Grantsburg and with Victrex as a whole has been daydreaming with these ideas of how can we take this, apply it to the gearing industry, again, to make more market space and to understand how do we capture more market with how we can make polymer gears. So one of the first ways we wanted to talk about was with a strain wave or harmonic drive gear. So this generally is made out of a metal, and the whole component is made out of metal. And what we were able to do is with that tape laying was come up with ways that align the fibers so that we have a tuned strain wave gear for how it's going to perform. Now, if you think about it, carbon fiber is very stiff in its direction along the length of that tape. And if I put all the tape in the vertical direction, I would have excellent strength this way for like a tensile load, but really no hoop stress, no circumferential loading could happen. It would just break apart the layers. If I put everything in the circumference, I would have great hoop stress, but maybe not what I need for insertion. And so because you can layer that, you can change the angles of how you're braiding that or laying it down so that you can fine tune the stiffness that you want in your tube. And this allows you to compete or make a system that you would not be able to make out of metal because you can change how that is going to behave inside a system. And so we've built some prototypes of these. We have the flange and tube made out of a composite. We consolidated that with a PEEK gear around the outside and then hobbed in the gear to create the gear teeth. This is a picture of that strain wave box in a test fixture prior to it going on to the quasi-static dynamometer that we showed in the testing rig. Another way that we've looked at composite gearing is with a patent application here listed on the slide. And what this is we're aligning the carbon fibers around the outside circumference of the gear in a way that's manufacturable and kind of looking at how the carbon fiber performs. We've made some small test rigs with sample plaques to simulate a gear tooth to try to understand what's going on. And with that performance we had from the small test plaque and the understanding of the composites, we're expecting to see the performance for a fatigue curve significantly improve on the composite gear solution. So this is a simulated understanding of where that might be, and we're looking to build and test parts in the future so that we can understand exactly where does that lie. And this would allow us to capture or move into that larger market space with a composite gear. Now, when you think about how you manufacture gears, I'm assuming most of you hob gears or use traditional manufacturing methods. We're not limited by the hobs that we use, and we're only limited by what we can put into the steel and then the plastic that we're using to generate the parts. So maybe you've noticed on the slide deck as we're going through that our gear shapes don't always look like what you're used to seeing in a hobbed gear or a metal gear, we'll say. So generally you have a land and then your teeth are very set ratio from the pitch circle up and the pitch circle down on where those are going to be. In a polymer gear, We extend that out. We try to increase the contact ratio as much as we can, minimize top land, and we're focused on root geometry as well. So kind of this concept of how do we design the gear, what's that ideal gear shape going to be? If we can transfer it into the steel and it goes through the design for manufacturing process, we can kind of make all sorts of shapes in a mass production environment. And I have a few examples of those to look at in the next slides. So generally these are fairly small parts here to demonstrate what we've got, but these are very, very small parts manufactured out of a carbon-filled PEEK, which is why they're kind of this black color. Natural PEEK by itself sort of has a tan or a khaki color. And these are just a few different applications that we have. So helix angles can be quite steep to worm gears. We have features that can be molded into the parts. So little hubs for bearings can be molded onto them. Obviously, we can make some oval shaped gears as well. And then we talked in the past around metal inserts. So we do have gears that need to press fit onto a shaft and be located in place, a keyway for torque transmission. Plastic can't always accommodate that. And so you have to understand not just your gear meshes requirements, but your parts requirements and what you might need to do when you're making your plastic part. And so in some instances, we use a metal insert to accommodate that. In other cases, you can mold a feature directly into the part for locating a shaft or a bearing, whatever you might need for your housings. So I think what I was trying to convey throughout this slide deck was Victrex is looking for that market space. How do we help you to use PEEK in industries around the world? And so we're looking at what do our customers need, how do they need to expand, and taking that R&D effort and looking to grow the markets for both of us. Because together we can make more space and we can work to push what gears can do in polymers. And so I thank you for your time. I really appreciate you taking the time to join us today. And I'm available for questions now. Thank you.